And it's a pleasure to be here. Okay, so I'm going to talk about quasi-graphic matroids, and it'll be a while before I get to that, but I'll begin with a quote from Bill Tutte. I think it's appropriate. And I've thought about this quote quite often, and I have my issues about it. So if a theorem about graphs can be expressed in terms of edges and circuits only, then it probably exemplifies a theorem about matroids. Now, you could, in some sense, I think it makes, if you think about what Bill Tutte was probably trying to do when he was thinking about matroids, he was trying to think about putting planar duality into a more general context. That quote makes a lot of sense. And actually, but you can ask the question in a more general thing, was Tutte right in saying that? And if you want a good case for the affirmative, that Tutte was right, you should see, for example, James has got, which I sort of managed to bring up in 10 seconds on the internet when I was actually looking for that quote. And it's a very nice paper of James's on the interplay between graphs and matroids. And in some sense that, I would say, James can tell me if I'm wrong, but I'd say that quote of Tutte's is sort of what the continuing theme of that is. So that's sort of true, I mean, in many ways, and if you go to James's paper, you'll see many examples. On the other hand, if you think about paving matroids, which are, so for those of you who don't know what a paving matroid is a matroid that has the property that every circuit has size, the rank of the matroid, or the rank of the matroid plus 1. So there are no small circuits. And the conjecture, and it's a conjecture that everyone who's ever thought about this thoroughly believes, is that in the world of matroids, paving matroids basically completely dominate. And there's not much that paving matroids have in common with your typical graph. You might ask which graphic matroids are paving, and so there's this other sort of sense in which the world of matroids, there are all these weird beasts in the world of matroids that don't seem to exemplify Tutte's dictum. But so I guess that I would say that what I think of, and I've come to think of over time, is that many genuinely fundamental classes of graphs that are fundamental for one reason or another, not just fundamental because we're trying to generalise from graphs to matroids, but many genuinely fundamental classes of matroids actually do exhibit some graphic structure. And that's what I'm hoping that if nothing else, that you'll get out of this talk. So I want to begin with my first encounter, and this is a long time ago, and it sort of makes me, I don't like to think about how long ago this was, but it was a long time ago. And it was my first encounter with which was with matroids that did somehow exemplify graphic structure, and yet were also fundamental for some reason or other. Just to make it clear, because different types of graphs and different types of matroids associated with graphs will be talked about in this talk, obviously. When I talk about a graphic matroid, I mean the normal cycle matroid of a graph. So if I say blah is a graphic matroid, I mean that's the normal cycle matroid of a graph. And I mean, I think that everyone here would know that there is a canonical matroid associated with a graph where the cycles of the graph are the circuits of the matroid, and that's a cycle matroid of the graph. So that's one example, by the way, of graph matroids that exhibit clear graphic structure. I don't think I need to go into any more detail on that example. Okay, so my next example is a class of matroids which I'll call framed matroids. And a framed matroid is a matroid that's got a basis, and it has the property that every element in the matroid, for every element in the matroid, I can find a pair of elements in the basis such that that element is in the span. And the way I think about a framed matroid is just take a simplex in n dimensions, and that's your frame, and you're allowed to put matroid elements on the edges of that simplex, right? So the matroid elements in this case are points, and the lines of the simplex join vertices. They're my matroid elements. So that's an example of a framed matroid. A frame matroid is a matroid that can be embedded in a framed matroid, right? So the matroid on the left is a frame matroid. And the matroid on the right is a framed matroid. Those two things on there, the red and the blue, are meant to be parallel points in that matroid there. And that thing on the right proves that the thing on the left is a framed matroid. Now, obviously, it doesn't take much thought to see that if you give me a frame matroid, there could be a variety of ways that I could frame that matroid. And that leads straight away to one of the difficulties in working with these things, is that you get inequivalent representations of framed matroids. But I'm not going to say anything about those difficulties, but issues like that cause problems. All right, now one thing is, it should already be clear to you, when I talked about framed matroids, there is an obvious graphic structure going on. It's just, instead of saying the basis B for the frame, I could have called those vertices of a graph. And in elements of the matroid, if it's parallel to one of my basis elements, I could make that a loop at the vertex. And if it's not parallel, I can make that an edge joining the two points of the basis that span it. And the thing on the right is just a different encoding of the same information as on the left. There's no difference, except the thing on the right is a graph, so yeah, obvious graphic structure. So straight away from framed matroids, we see that there's an obvious graphic structure there. The graph, though, does not give me all the information about the original matroid. There are some if I give you a framed matroid, so like that one on the left, there are some dependencies that are forced by the frame geometry. For example, if I have two basis elements and I have 3 points on that line, those 3 points must be dependent. I've got 3 points in rank 2, got to be dependent. That purely comes from the frame geometry, right? So that's, or another way of thinking about that, I'm using geometry language, I could use graph language instead. That's something I could see from the graph. If I get 3 parallel edges in the graph, that's got to be dependent in the matroid, the frame. But the graph doesn't give me all of the information about the dependencies. And so, for example, in that example there, that's a framed matroid, and I've given you those green lines indicate that there's a dependency going on there with those other things, but that's not information that comes from the graph, right? Those dependencies are extra facts about the matroid that you don't immediately get from the graph. So in general, there's a graph that gives you information about a framed matroid, but the graph doesn't tell you the whole story of the framed matroid, right? But they do have, but the thing is that at this stage it is clear that they do exhibit graphic structure in this sense. Now, my first encounter with these types of matroids was in a completely different language, and I really struggled to understand the paper but it goes back a long time, but it wasn't as far back as 1973 when I was struggling with this paper. But it was Dowling group geometries, and Tom Dowling described a class of matroids that you could associate with any fixed finite group. And the dependencies in the matroid were induced by group multiplication. Now, the trouble was that Tom wrote this paper using lattice theoretic language, which was quite common in matroid theory at the time to write stuff using lattice theoretic language, which I didn't understand very well at the time. And then I thought that these were very, very complicated objects, these Dowling group geometries. And then one day the penny dropped as to what was really going on. All that was really happening, well, when I say all that was really happening, I don't want to belittle what Tom did, because it was a really nice insight. But he said, if I to get a very simple example of a Dowling group geometry, what you do is you take your favourite finite field, say GF11, and you take a basis in that finite field, and then you get the frame geometry by adding all of the points on lines joining pairs of elements of that basis. Right? And that gives you a unique matroid. I mean, there's lots of bases you could choose, but they're all, it doesn't matter which basis you choose, you'll get the same matroid. And that matroid that you would get by doing that operation. It's clearly a framed matroid because I described it to you as a framed matroid. And that matroid that I get by doing that operation is the Dowling, whatever the rank was, it's the Dowling group geometry of that rank over the group of the multiplicative group of the field. So in that case, my field was GF11, so it's over the cyclic group of 10 elements. And the interesting thing about that is even though I did that construction, and this is what Dowling proved, even though I did that construction using a field, the fact is that the only information I needed to understand the full set of dependencies in that matroid was the only information I needed to know was the multiplicative group of the field. The field addition plays no role in that thing. So that was an example that comes directly from fields, but you can do this from an arbitrary finite group, abelian or non-abelian. And so there's the operation. That's what, I mean, you get this matrix where you've got at most 2 elements in every column. So that's how one constructs Dowling group geometries. If I take the 2-element field, the multiplicative of the group of the 2-element field is the trivial group. So I've only got, you know, when I do that framed matroid, I only get 1 point on every line. And it turns out what I'm constructing is the cycle matroid of cliques. So the Dowling group geometry for the trivial group is a cycle matroid of cliques. For other groups, it's a more different structure. So what's actually happening is the Dowling group geometry, what the group is telling me. Remember, I said in a framed matroid where we could think of it as having that graphic structure, but you've got the vertices and all the points are on those lines. Some of the dependencies come just from that simple geometry in the simplex, as it were, and the other dependencies, I'm getting that information about the other dependencies from multiplication in the group. And it's not difficult. It's an easy exercise to see how it works, but I'm not going to go into the details of it. All right, so we can think of that as giving us another class now. Instead, we can, as well as talking about matroids representable over fields, where for the purpose of this talk, if I say a matroid's representable over a field, I just mean it's essentially a simple matroid, no loops or parallel edges, it's just a submatroid of a projective geometry. And if I want to talk about, I can also talk about matroids representable over groups, and they're just the things that I get as minors of Dowling group geometries. One thing that I didn't say, and I should say now, is that the class of frame matroids is minor closed. And the class of, that's just where we're dealing, or in any unexplained context, the classes I'll be talking about will be minor closed. So just something to be aware of. All right, so what happens when we take minors of, so we take these Dowling geometries, and if we take minors of Dowling geometries, then that gives us what we'll call a matroids representable over a group. But the important thing is that when I take a minor of a Dowling geometry, so it's clear if I delete, but if I contract elements from a Dowling geometry, I still get something that's a restriction of a smaller, lower rank Dowling geometry. So in the world of Dowling geometries, there's always this boss, this dominant thing, which is the one that everything's a subgeometry of, right? That's a simple way of saying it, I suppose. And the thing that got me, why I thought that Dowling geometries were really interesting is because of this theorem of Kahn and Kung's. And this theorem is actually, I think it's one of my favourite theorems in the whole of matroid literature, because I think it's a truly seminal theorem. The theorem says what it says, but it's saying something, it's really saying that structurally something's out there, something is going on. Structurally something is going on in this wide world of matroids, which is such a much bigger world than the world of graphs. So what did Kahn and Kung do? First of all, we say, what's a hereditary class? A hereditary class, I'm just going to do a few definitions before I can state the theorem. So a hereditary class of matroids is a class of matroids that's closed under minors, okay? And it's got this other operations being closed under direct sums. Well, that's not asking you much, really, is it? being closed under direct sum. So it's a minor closed class that's also closed under direct sums. And a sequence of universal models means it's a sequence of matroids, one for each rank, and that's just with the property that every member of H is a restriction of one of these. So in the world of graphic matroids, cycle matroids of cliques would be a sequence of universal models for graphic matroids, right? And Dowling group, the full Dowling group geometry over a particular group where I have all of the possible elements, that's a sequence of universal models for the matroids representable over that group, right? And projective geometries over finite fields give a sequence of universal models for matroids representable over a particular finite field. And what they said was that a variety is a hereditary class with a sequence of universal models. And their theorem is, I've just told you all of the varieties that there are. Examples. And that's just repeating what I've said. And the theorem says, apart from degenerate cases, and the degenerate cases really are degenerate, those things there are the only varieties. They're the only classes of matroids out there with those properties. So there's something fundamental going on. Now, we all recognise that projective geometries over finite fields are fundamental. I mean, that's just straight clear. But the fact that the only other things that you get are these matroids representable over groups, and there's nothing in between, is the thing that struck me as mysterious and very powerful the first time I encountered it. And there's a few things there to sort of, so that's telling us, okay, so that really does relate to the theme of this talk, just to sort of make a meal out of it. That is telling us the matroids representable over a finite group exhibit graphic structure, and here are classes of matroids that exhibit graphic structure that play a key role in what's obviously a significant theorem. So that's clearly something fundamental about classes of matroids with graphic structures. And a few things that are sort of worth thinking about there. The first is, why aren't there any hypergraphic varieties? So there's whole projective geometries, and then these ones that come from graphic structure. And, well, instead of actually talking about framed matroids where I could just only allowed to put points on lines of the simplex, well, I could talk about hyper-framed matroids where, let's take 3 hypergraphs, where I'm allowed to put points on faces spanned by 3 elements of the simplex. And I could do that. And that would give me a class of matroids, and it does. You can just look at those classes of matroids. But it turns out that those classes, when you go from 2 to anything bigger, it turns out those classes of matroids are not minor closed. And you just, when you start contracting elements, depending on how you think about it, but you start to see yourself inevitably somehow throwing elements onto higher rank faces, and you can't avoid it, so you don't have minor closed classes. So the hypergraphic varieties somehow do not appear. And that's sort of, that I remember to this day the first time when I realised that was it, somehow not true. And the other thing about that is that there's a question like, Cogs' theorem is a theorem about very particular classes of matroids, but what can you say, is it telling us anything about more general classes of matroids? And Cogs' growth rate conjecture, which is now a theorem, but Cogs originally, at the time, was sort of, again, at the time was a conjecture that surprised me when I thought, how could this be true? But then, I think it was reading about that conjecture got me thinking about some of these things, but I forget exactly how it went. But Cogs' growth rate conjecture, says that if I give you a class of matroids, the growth rate of that conjecture is the size, a measure of the size of the maximum number of elements of a simple rank R matroid. And it's the function that measures that, how many elements you've got. Now, Kuhn's conjecture was that that function is either linear, so that you've got at most a linear number of elements in terms of rank, or quadratic, where you've got a quadratic number of elements in terms of rank, which is what we see in graphs. Tricky, you know that a clique has n choose 2 elements, so that's what we see in graphs, and it's what we see in general for Dowling group geometries. We see quadratic growth rate conjecture, and then quadratic growth rate, and then above quadratic is what we would see for projective geometries, which is exponential, and Kuhn conjectured that there were no other growth rates, and Kuhn's conjecture is true. And that, again, was a remarkable conjecture to make at the time, I think. It's still a surprising thing in my mind. And the other thing, and I asked Kuhn about this, I said, why did you put, it was a silly question, once I'd heard the answer. I said, why did you put that direct sum condition in the definition of variety? And Cogs said, well, we couldn't prove the theorem without it. and that's actually not just that they lack the ability to prove the theorem without it, is that the theorem is no longer true without the condition. So, and the direct sum condition might seem a little bit, in some ways it's not artificial, because it's somehow a weak property to say that something's closed under direct sums. Yet if you don't have the direct sum condition, all sorts of quite natural classes arise that would be varieties without this direct sum condition. But at least for matroids representable over finite fields, these classes are actually related to, at least the ones with quadratic growth rate, are related to Dowling geometries in some sense. They're sort of, I'm going to use some jargon here, but they're somehow low-rank perturbations of Dowling geometries, so that what we see is that even though they don't exhibit exactly the same explicit graphic structure as the Dowling geometries, qualitatively, Kahn and Kuhn's theorem is telling us something that's sort of qualitatively true for much bigger classes. If that made no sense to you, don't worry about it. You don't need to know anything about it for the rest of the talk. All right, so the actual explicit description, so if we think about the graphic structure, we don't know the graphic. I'll just go back a little bit. When I said that, so I gave you the example of Dowling group geometries just as an example of a class of frame matroids which are fundamental, and the class of matroids that we can associate with graphs that are fundamental. But the actual group structure, I'm not going to think about ones that come from groups at the moment. I just want to go back to the general question about frame matroids. So when I talked about it before, I said that a frame matroid has an association with it, and that graph tells you some of the dependencies in the matroid, but not all. And Tom Zaslavsky made an extensive study of precisely what you have to say in the graph to describe all of the dependencies. So I'm just going to quickly talk about that now. So what's a theta graph? A theta graph is just 3 paths joining 2 vertices. And a theta graph contains exactly 3 cycles, as is clear there. And what Tom described is the notion of a biased graph. And a biased graph is a graph with a particular collection of cycles, which we will call our balanced cycles. And the property that you ask of the balanced cycles is that no theta subgraph contains exactly 2 balanced cycles. So if you contain 2 balanced cycles, it forces the other one to also be balanced. And why is that interesting? It's interesting because we can, given a biased graph, we've got all the information now to describe an associated frame matroid. So just given a graph, there's an associated frame matroid, but there's more than one because the graph doesn't give me all of the information. But if I give you a biased graph, I get a frame matroid. And I just say that the independent sets of the frame matroid are the sets that contain no balanced cycles, and for each component of that graph associated with that set of edges, we have no more vertices than edges. And that gives me the independent sets of a matroid. And it's a straightforward thing. So, and the theorem is, so Tom's theorem is that every biased graph gives me a frame matroid in that way. And not only that, we capture all frame matroids by biased graphs. So the answer is that frame matroids, the description of frame matroids as a class with graphic structure is that we just have to talk about bias graphs instead of graphs, and we explicitly capture all frame matroids. Right. So that's frame matroids. And just so notice with a frame, with a bias graph, we've got cycles. Some cycles are balanced. The ones that are not balanced we'll call unbalanced, and all of the cycles are balanced. Then we get the cycle matroid of the graph. So that's just the normal thing. All cycles are balanced. So every cycle is a circuit in the matroid. And the balanced cycles are circuits in the matroid. The unbalanced cycles are independent sets in the matroid. We'll talk a bit more about later what the circuits in the matroid will look like. If all cycles are unbalanced, then we get a matroid that many of you will be familiar with, I'm sure, and that's the bicircular matroid of the graph. So we've got all cycles balanced, the normal cycle matroid, all cycles unbalanced, the bicircular matroid. There are many, many, many possibilities in between. If I want to describe Dowling group geometries as in this way, what I'll do is I'll just take a graph and I'll put group elements on the edges, and I have to direct the edges. And then I have a rule for using the group multiplication to tell me which cycles are balanced. So when certain group elements multiply together to give 0 around the cycle, and then give the identity when I'm around a cycle, then they are the balanced cycles. So the group multiplication induces balanced cycles, but I don't have. And that's nice in the sense that that's easy to certify, because I can polynomially give you the information. In general, for a biased graph, I've got to tell you that this exponentially large list of cycles, which ones are balanced and which ones are not, so it's problematic in that sense. But that's a fact of life, because there are a lot of matroids out there, so you're never going to find an economical way of describing them all. And here's another fact which is really important for what will come later, is that disjoint unions of unbalanced cycles are independent in the frame matroid. So disjoint unions of unbalanced cycles are independent in the frame matroid. So if I've got an unbalanced cycle there and an unbalanced cycle there, they're both, the union of those two things is independent. All right, so that's one class of matroids that have clear graphic structure, and that's the class of frame matroids. Another class of matroids that has clear graphic structure is the class of lifted graphic matroids, and there's a picture there that describes what's going on here. So a lift of a matroid, so in this example here, the middle matroid M prime is a lift. The matroid on the right, just before the graph, will come to the graph in a minute, but the matroid on the right just is 4 parallel pairs of elements in rank 3, and then I'm lifting it. If I contract E, I get the matroid on the right, and then if I delete E, I get the matroid on the left, and the matroid on the left is a lift of that matroid on the right, and the matroid in the middle is the matroid that proves it, right? So that effectively what I'm doing is lifting up that and throwing away the element that I did it with. And that's a lifted graphic matroid. Why is it? Because this matroid here is the cycle matroid of that thing on the right, the graph on the right. So that's just, so all a lifted graphic matroid is you just take the cycle matroid of the graph, the good old familiar matroid and do a lift of it. And that gives us a class of matroids that we might or might not be interested in. One person here that might be interested in matroids of that type is Bertrand. I think he's going to talk about even cycle matroids later on. So an example of a lithographic matroid is if I just take a matrix over G of 2, so this is in the world of binary, I look at with most 2 non-zero entries in each column, then that will always represent the cycle matroid of the graph. Right? I mean, it's just the, I always forget the names of these matrices, but it does represent the cycle matroid of the graph. And if I add an extra row, that creates, so that top row of 1s, that's a lift of that cycle matroid of the graph. Because to get the graphic matroid, I could add a column consisting of 1 and a bunch of zeros and contract that. That effectively deletes the top row. So adding rows to a representation gives me lifts of matroids. And that's a lithographic matroid. That's an example of the even cycle matroid of the graph. And the reason that's an example of the even cycle matroid of the graph is if I give you a cycle in the original graph, for that to be a circuit in the matroid, I have to have an even number of 1s, and that's just an easy exercise to see that. So the balanced cycle, the cycles of the graph that are circuits in the matroid are the cycles with an even number of 1s. So that's, oh no. Yeah. So one way to get, and it turns out that as well as getting frame matroids from bias graphs, we can get lifted graphic matroids from bias graphs. There's no difficulty here at all. We just have a slightly different rule. So we start off with our bias graphs, with our set of circuit cycles, such that no theta graph contains exactly 2 balanced cycles. And same thing, but we have a slightly different rule for getting a matroid. And the slightly different rule says that we define our independent sets. If a set's independent, if it contains at most 1 cycle and no balanced cycles. So we have a slightly different rule for getting the independent sets, but that way we get a lifted graphic matroid from the bias graph. And then Tom proved that every lifted graphic matroid can be obtained in this way. So from bias graphs, we've got 2 genuinely interesting classes of matrices that we can get. And what's the difference? And the thing to think about is that if I give you a disjoint pair of unbalanced cycles, so I give you a pair of cycles that are unbalanced and they're completely disjoint, then that will be a circuit in the lifted graphic matroid and it will be independent in the frame. It started buzzing on me. It's acting like a phone, this thing here. I'm getting frightened of it. But, so, okay, so that's, just keep that in mind. Right? You have bias graph and frame matroid, lifted graphic matroid, subtly different rules, but the point is, the key thing is that a disjoint pair of unbalanced cycles is a circuit in the lifted graphic matroid and independent in the frame matroid. And so that's just an example, which I realised when I was looking at these slides, I labelled correctly. So if I look at the pair, the things that have got labels, I chose the optimally bad thing of labelling a subset of those edges. But if we look at so that's a graph, all circuits are unbalanced, all cycles unbalanced, right? The thing on the left is the frame matroid, the thing on the right is the lift matroid. And for example, if you look at CD and the opposite pair, so you've got 2 pairs of 2 element cycles, you'll see that they're independent in the frame matroid, but they form a circuit in the lift matroid. And there is something else too. If I look at the set A, B, C, D, right, so those edges A, B, C, D, and then if I look at the loop, not the one I've labelled, the unlabelled loop, you will see that the unlabelled loop is in the closure of A, B, C, D in the lived matroid. And that's a little bit surprising because you've got this loop in a different component and it's in the closure of A, B, C, D. But it is, in the lived matroid you can see that both loops are in fact in A, B, C, D. Weak frameworks, right? So basically I'm starting to get onto the work that Jim and Bert and I have done, and the notion, we introduced the notion of framework. But we have to start with weak frameworks before we come to frameworks. So what we're trying to do is something, we've seen what Zaslavsky's done, but we're trying to do something that sort of gives a slightly more unified picture of what's going on. So we say, give me a graph and a matroid, then I'll say that the graph is a weak framework for him if the following holds. Well, condition one is a no-brainer, right? It's just they've got the same set of elements of the matroid the same as the edges of the graph. Condition two just is a natural condition for each component of the graph. The rank is less than or equal to the number of vertices. It's just a... condition three says that if I look at the... If I look at a vertex, and if I look at the closure of this set of edges, then the only thing I'll pick up in the matroid, so this is I'm looking at the vertex in the graph and I look at the closure of this set of edges in the matroid, the only thing that I could pick up in the closure of that is I could possibly pick up this loop. And we saw an example of that in a lift matroid where that happened. So that the only thing I could possibly pick up in the closure of that set of edges is I could possibly pick up a loop. If I didn't have any loops there, that's telling me that this set of edges here is a union of co-circuits in the matroid. And in the generic case, it's telling me that this set of edges will be a co-circuit in the matroid in the generic case. So that's the sort of thing to keep in mind there. So that's what condition 3 is trying to say. And, whoops. No. Oh, right, so I've repeated that picture just to illustrate some of those things, but I'll move on. So being a weak framework, by the way, if you give me a graph and a matroid and you say, is it easy to test whether it's a weak framework? The answer is it's very easy to test, right? You only have to do a very few, relatively small number of rank calculations and check how things work with the graph. So that's a nice fact about weak frameworks. Another fact about frameworks is if something's a forest in the graph, then it's independent in the matroid. And another property is if A is a subset of E and the number of vertices in the graph, in the subgraph induced by A is less than the cardinality of A, then A is dependent. So we can see that it's giving us quite a lot of information about the matroid. And Paul has this nice theorem that says essentially, with this subtle extra thing on the rank condition, that so it's a slightly stronger condition, but the point is that to test whether a matroid is graphic, and that this is to test whether a given matroid is the cycle matroid of this graph, you only have to test that that graph is a weak framework for the matroid with a bit of extra structure to force it to have low enough rank to be the cycle matroid of a graph. So the actual idea of thinking about weak frameworks really came from that theorem of Paul's. Okay, so we can, in the world of weak frameworks, we can come up with the notion of balanced cycles. We'll say, give me a weak framework for a matroid, then any cycle of the graph that's also a circuit in the matroid we'll call a balanced cycle. So in the world of weak frameworks, we've got balanced cycles, and it's easy to check that the balanced cycles must satisfy the theta condition. That just comes from matroid properties. Oops. So you've got nice properties about weak frameworks, and we actually thought we had a lot of nice properties about weak frameworks, but it wasn't that nice. And at the time, this is a few months ago, not that long ago, Darryl Funk was doing a postdoc in Wellington, working with Dylan Mayhew. And Darryl turned up to my office one day and said, I've been trying to understand this stuff about frameworks and things like that. And there's something I can't understand. And you know, here's this young postdoc and here's this senior, you know, professor. And I said, look, you know, it's all a bit tricky. You've got to look at the definitions carefully and you've got to think hard about these things. And Darryl wasn't convinced by my explanation. And so after a little while, I did the very rare thing and I actually started listening to what he was saying. And that was a mistake. But actually what Darryl had done was he'd actually proved the fundamental theorem of weak frameworks, which is that every matroid is a weak framework matroid. So you give me any matroid you like, there exists a graph which is a weak framework for that matroid. Now you can look at this theorem as saying two things. You can say, oh, that's a proof that every matroid exhibits really clear graphic structure. Or else you can see it as a proof that the concept of weak frameworks is not quite the right concept. So how did Darryl's example go? He said, here's a graph. You just take a bunch of vertices and put a loop at each vertex. And in that case there, I've got 6 loops. Give me your favourite matroid with 6 elements and put a matroid element at each edge. And then that graph is a weak framework for your favourite matroid. Now, it's clear what the problem is, that we somehow had that there's always in your mind when you're thinking about these things, you're not thinking about graphs with no connectivity whatsoever. We were subtly using some connectivity properties of a framework, and that actually we were cheating at one stage. So thanks for proving, wherever Darryl is, thanks for proving the fundamental theorem of weak frameworks for us. So we have to tighten up the notion of a framework slightly. So, which actually caused a bit of grief for us for a little while, but it's not difficult to do. You just have to add an extra axiom that gets you past that degeneracy. That's the thing that you need. And this is the way we chose to go. So what we said is a weak framework is a framework if for each circuit C of M, the subgraph induced by C has at most 2 components. And you see that bunch of loops, if you give me a circuit in the matroid, then the subgraph induced by that circuit in the graph is just a bunch of loops, so you'll have lots of components. So that gets you out of the problem. It's slightly annoying because there are exponentially many circuits, and so to check that something is a framework using the definition, you have to live with that annoyance. But in fact, you get past the issues by a bit of connectivity, and I'm not going to say much about that. So we'll say a matroid is quasi-graphic if it has a framework. And I've just talked about that. All right, so what we get is that if I give you a bias graph, and so going back to the original Zaslavsky type approach, then if you give me a bias graph and you consider the frame matroid, then G is a framework for the frame matroid. So the frame matroids are quasi-graphic. So quasi-graphic matroids are matroids that have a framework. And lift matroids are also quasi-graphic. So lift matroids are also quasi-graphic. And what is the difference? Well, and again, this goes back to something I was talking about before. We've got a framework, and we've got lift matroids, and frame matroids are quasi-graphic, but what's the essential difference between the two? If you give me a framework for a matroid, and in that picture there are no balanced cycles, all those cycles are unbalanced, then those things are always circuits in the matroid with that graph as a framework. So just looking at that, I know those things are circuits. But the key ambiguity comes from, and I'm repeating myself, the key ambiguity comes from exactly what was going on before with the difference between the frame matroid and the lift matroid of a bias graph. The key ambiguity comes from disjoint pairs of unbalanced cycles. If all such pairs are independent, then we get the frame matroid. And if all such pairs are circuits, we get the lift matroid. Well, what's the other possibility? The other possibility is that some such pairs could be independent and some such pairs could be circuits. And that could give me a matroid with that framework that somehow things are a bit weird. And so the question is, are there intermediate examples? And the answer is, sure, there are easy low connectivity examples. And so when someone says, okay, yeah, of course, if I give you the direct sum of a lift and a frame matroid and blah, blah, blah. So what I want to say is that's boring. Let's factor out the low connectivity degeneracies and raise up the connectivity a bit to get to more interesting situations. And 3 connectivity will be enough for us here. Then the answer is that it's easy to find cases where there are not intermediate examples. It's easy to find cases where there are not intermediate examples. So if I give you a framework and I tell you that framework has an unbalanced loop, then the only, and it's a 3-connected matroid, right? So at the moment, if I don't, all matroids will be 3-connected for the moment. It's a 3-connected matroid, and if I tell you that my framework has an unbalanced loop, so an unbalanced loop just means I've got a loop and I'm telling you that that's unbalanced, then the only matroids with that as a framework are the bias matroids or the lift matroid. There are no intermediate examples. There are no intermediate examples. Now, the actual proof of that's not hard, but I'm worried about time, so you'll just have to, so time will run out on me. So I was hoping to go through it, but I can't. And another genuinely surprising example still to me is the same holds true if I give you a representable matroid. So I just give you the information that the matroid is representable, and then I tell you that if it's quasi-graphic, so it's got a framework, then that matroid is either the frame matroid or a lifted graphic matroid. There is nothing in between. There's only frame matroids or lifted graphic matroids, nothing in between. And that's just for representable. It doesn't matter which field or anything like that. That's the theorem for representable matroids. So you can ask, is that all there is? You know, we only need an unbalanced loop, we only need representability. And the answer is no, it's not all there is. And the reason it's not all there is you can have a graph. We have this thing which is called relaxing a circuit hyperplane. So a circuit hyperplane of a matroid is a set which is simultaneously a circuit and a hyperplane. So it's closed, and there's an operation that you can do. If you give me a matroid with a circuit hyperplane, then this operation is at the basis of probably about 80% of the sort of things that I'm going to talk about, this type of example I'm going to describe now. You can take a circuit hyperplane and you can relax it. In other words, turn it into a basis. It's got the right number of elements to be a basis. You can turn it into a basis and make no other changes, and you still have a matroid. Now, if I look at that graph, those set of bold edges, and so there's 2 cycles. There's a cycle at the top and a cycle at the bottom, and then there's that bipartite stuff in between. There's a set of bolded edges and a set of dotted edges. If you look at that set of bold edges and that set of dotted edges, that's a disjoint pair of circuits that hits every vertex. So that, and it turns out that set of edges is a circuit hyperplane in the lift matroid, because it's a circuit in the lift matroid, and it's independent in the frame matroid. So if I take the lift matroid of this thing and just turn that into an independent set, I've got a matroid that's not a frame matroid and it's not a lift matroid. I've just this. So I've actually given you a proof that this matroid is not representable, by the way, because it would contradict our previous thing. And it turns out that in this particular graph, there are many such circuits like that. And in fact, there are exponentially many in terms of the size of the graphs. Whoops. And with construction like that, it's not only that so the question is that all there is in the world of framework matroids, quasi-graphic matroids, sorry, if I'm representable and three connected, I'm either lift or frame, but if I'm allowed to go to the non-representable world, almost all the matroids live in the intermediate space between being neither lift nor frame. And I can take that particular graph and generalize that to get a theorem which says, in essence, that to test that you can't even test, you cannot test whether a matroid is a frame matroid in polynomial time, because you can find these examples with exponentially many of these circuit hyperplanes, and we can relax an arbitrary subset of them to obtain a matroid which is neither lift nor frame. So that shows you that the world of frame matroids is unfortunately difficult, but the difficulties seem to lie within the class of quasi-graphic matroids. And it's the same as for the world of lifted graphic matroids. That's unfortunately difficult, but the difficulties seem to lie within that world of quasi-graphic matroids. Jim and Bert and I have a conjecture that there's a polynomial time algorithm that, given a three-connected matroid, M via its rank oracle decides whether M is quasi-graphic. So what I really want to finish off by saying is that, in some sense, intractabilities arise for frame matroids and lifted graphic matroids, but if we just go to the general setting of quasi-graphic matroids, a lot of those intractabilities should disappear. You could ask similar questions about excluded minors, about how many excluded minors you might expect for frame matroids and things like that. But I won't say anything about that, because if I were to do that, I would be stealing the thunder of some of the speakers later on this afternoon, and I don't want to steal their thunder. So thank you very much.
All right, are there any questions? Maybe I have a question. I think, how does this extend Zaslavsky's work about like lift versus frame and stuff in between?
Well, I think the thing is that Zaslavsky tended to focus on lift matroids or frame matroids. But, and I mean, it's really a question of perspective. I mean, Zaslavsky did ask questions about whether or not intermediate matroids could exist, but this is, so it's, I don't really know how to answer that question. I might be gaga, I might be jet lagged, yeah. I am jet lagged, yeah. Paul, sorry.
Going back to what you were saying about graphs, with your balanced cycles and unbalanced cycles and every theta, there's no theta with exactly two balanced cycles.
Yeah.
So, I mean, is there any hope of a theorem describing those things? You said no, but is that what I mean, I'm thinking if you put group weights on the edges and look at the cycles with sum to zero in the group or product to zero in the group, that would give you such a thing.
That does. Yeah, if you put groups on the edges, but no, I don't think so. No, they don't. They don't all arise that way, that's for sure. Now, there's a question, I mean, this is a bit related to Peter's asking. The question is if you, there's a question of what happens if you make the graph very rich, right? And then,
is it easy to say they don't polarize that?
Yes.
Yeah.
Yes.
Yeah.
I can give you an answer afterwards, but yes.
Yeah. No, well, there's no chance of a description in general, but actually Peter's been thinking about a related question, and he would be the person to talk to, yeah.
artificially come up with constructions.
Yeah.
That's sort of my thought. From a structure theory point of view, you don't like classes where you can top up the conics and use that force construction. In this class, you can do it. You can take some crappy examples and make it one or the other.
It's a question.
Are there any other constructions that you know, aside from this relaxing the two disjoint spanning circuits for stepping outside of lifted graphic in between frame matroids and lifted graphic matroids?
There will be other constructions, I'm sure, but the thing about it is that the nice thing about the circuit hyperplane relaxation thing is that you can just do it and you don't have to check anything. Whereas if you're not a circuit hyperplane and you just decide to declare, you've got this problem, you just decide to declare this set of things to be, to follow the frame rule, and this set of things to be independent, and these pairs to be independent, and these pairs to be dependent, then you've got to prove that you're not actually getting, you've got to, it's got to be a matroid, and that's something you have to check. Whereas the circuit hyperplane construction just makes it a triviality to check. Yeah.